Sustainable chemistry focuses on the design of processes or products that use or generate less waste or hazardous substances. This is very important as it is aligned with the current efforts to fight global warming. As such, I present to you our contribution towards sustainable analytical chemistry. Good day, everyone. My name is Ncongwane under the supervision of Dr. Smit and Prof Ndinteh at the University of Johannesburg, South Africa. Our research is titled Automated Silylation of Flavonoids using 3D printed microfluidics. Flavonoids are a group of naturally occurring polyphenolic compounds. Reprinilated derivatives have been reported to show improved biological activities, and as of recently, more than 10,000 of these compounds have been identified and documented. These compounds are commonly found in plants and are obtained via extraction. Therefore, a technique known as derivatization is commonly used to study these compounds. In this technique, compound chemical and physical properties are altered to improve their performance in chemical analysis. Examples include alkylation, acylation, and silylation, which was used in this study. This brings us to our problem statement. Most flavonoids are polar, less volatile, and thermally unstable. They also have similar chemical structures, which makes it very difficult to separate. This is ideal for high-pressure liquid chromatographic analysis. However, HPLC uses large amounts of organic solvents, thus it is unsustainable. Alternatively, gas chromatography can be used. However, GC is only suitable for volatile and thermally stable substances. As such, to expand its application to polar compounds, derivatization, specifically silylation, is commonly used to make these compounds amenable for GC analysis. Like any other technique, it has its own limitations. Derivatization introduces extra preparation steps, leads to poor selectivity, and also uses expensive hazardous chemicals. In most laboratory settings, these reactions are commonly performed in batch, which is laborious and time-consuming. Therefore, to address the above limitations, we have adopted a few sustainable technologies to align derivatization with green analytical concepts. The first one is 3D printing. In this technique, an object is created by stacking layers of material in a layer-by-layer sequence. It was chosen because it is inexpensive and it is sustainable in that the objects created can be reused and customized rapidly. 3D printing can be and was used to manufacture microfluidic devices. These devices are used to exploit the physical and chemical properties of liquids and gases at micro or nanoscale, making them ideal for continuous flow chemistry since they use small amounts of reagents. Flow chemistry is concerned with conducting reactions in a continuous flowing stream by means of tubing or channels, which opens possibilities for automation of batch procedures, including safe upscaling in terms of an industrial application. The syringe pump system shown here on the screen, which is controlled by a computer and is connected to the manufactured microfluidic device, was also 3D printed. The parameters, such as temperature and stoichiometry, can be precisely controlled in this system, thus it makes it sustainable. This brings us to the aims and objectives of the study. The aim of the study is to automate derivatization procedures with the focus on the silylation of flavonoids. To do this, to develop a 3D printed microfluidic devices, derivatized model compound, quercetin, derivatized isolated flavonoids, and finally, derivatized plant extracts that are chemically complex. In developing the 3D printed microfluidic device, we used fused deposition modeling. Here, we designed the device using Fusion 360, an open source computer-aided design software. Then the device was then printed using a chemically resistant transparent polypropylene thermoplastic filament. The derivatization of quercetin was performed using N-methyl N-tertiary butyl dimethyl silyl trifluoroacetamide, also known as MTBSTFA, according to the schematic shown here. The silylation was performed both in batch and in continuous flow according to the conditions shown. Pyridine is commonly used in derivatization or silylation as a catalyst or a promoter of the reaction. However, due to its hazardous nature, it was substituted for acetonitrile. Our complete semi-automated 3D printed flow system functions in this way. It consists of two syringe pumps fitted with two syringes. Syringe A contains MTBSTFA and syringe B contains the sample quercetin. The two are introduced into the microfluid device via tubing, whereby they meet at the junction and mix rigorously. The microchannels where the reaction takes place are less than 1 millimeter in internal diameter. The device has a residence time of about 3 minutes at 200 microliters per minute flow rates. The product is then collected into the GC vial via the outlet, and together with the sample from the batch reaction, they were analyzed using GC, NMR, FTIR, and HPLC. For GC, both FID and 12MS were used. The conditions are shown on the table here. This was further, the FID chromatogram shows a peak at about 30 minutes belonging to the derivatized quercetin. According to literature, it is known that quercetin has a boiling point of about 500 degrees Celsius, which, when compared to the maximum temperature of the column, which is about 350 degrees, this peak was observed at about 320 degrees, which shows that after quercetin has been derivatized, the boiling point has been lowered, thus it was observed at about 320 degrees compared to its normal underivatized boiling point of about 500 degrees. This was further investigated on the mass spec, which showed that at about 28 to 30 minutes, the peak that we see belongs to quercetin that has been derivatized at least 5 times. Due to its high sensitivity compared to FID, another peak that contains at least about 2 silyl groups was observed at about 18 minutes. We further investigated this using FTIR. What we observed is that the underivatized quercetin was observed by a characteristic hydroxyl group at about 3,300 per centimeter. Upon derivatization, both in batch and in continuous flow, we observed the disappearance of the peak at about 3,300 per centimeter, which is characteristic to the hydroxyl group of the underivatized quercetin. Further, the presence of the tertiary butyl silyl group is observed at about 1,100 per centimeter. This supports the GC data that quercetin was successfully derivatized in continuous flow and that both the continuous and the batch method are comparable. We then further characterize this using HPLC, and we observed the appearance of 2 peaks for the derivatized quercetin sample compared to the underivatized quercetin, suggesting more support for GC and FTIR data presented earlier. For the purpose of this study or presentation, if I may, the NMR data, including the data for the other flavonoids that have been studied in this, have not been shown. And in that, by so saying, we would like to conclude by saying that we have demonstrated a sustainable alternative and semi-automated procedure for the derivatization of flavonoids compared to the traditional batch method. This is very crucial for improving throughput and capacity in terms of natural products. Technologies related to the fourth industrial revolution, such as 3D printing, robotics, and automation, were used. Designing of a procedure or procedures that reduce or eliminate waste is sustainable and in line with green analytical concepts. We thus have further also expanded the application of GC or polar compounds. In the future, we would like to extend our systems application to further study fuels and food products. We would also like to modify and optimize the system to work on multiple samples with minimal manual intervention. We would also like to apply the optimized system to a range of other flavonoids, including their mixtures and eventual raw plant extracts. By so saying, I would like to acknowledge my supervisors, Dr. Smith and Prof Ndinteh. I would like to acknowledge the Separation System Chemistry Group, the Analytical Chemistry Group, the Department of Chemical Sciences, the University of Johannesburg, and the National Research Foundation of South Africa for funding this research. Ngiyabonga, which means thank you in the South African Zulu language. I thank you.